All biological systems are aqueous. To understand the behavior of proteins or the function of a cell, we have to start with the quantifiable nature of water itself. Water is an amphiteric molecule. It can act as both an acid and a base. This characteristic is also described as amphiprotic, meaning it is capable of both donating and accepting protons. In any sample of liquid water, a very small percentage of molecules undergo a spontaneous dissociation, where a hydrogen proton transfers to another. This reaction leaves behind two distinct ionic components, the hydronium ion, represented as H+, and the hydroxide ion, or OH-. By deriving the mathematical constants of this reaction, we can define the pH scale and eventually map how biological buffers resist environmental change. The predictability of this dissociation establishes the mathematical foundation for every chemical interaction that occurs in a living system. To measure the extent of this ionization, we use an equilibrium constant, known as KEQ. This constant is defined by the concentration of the products, hydrogen and hydroxide ions, divided by the concentration of the reactant, which is the intact water molecule. At 25 degrees Celsius, the concentration of pure water is a constant 55.5 molar. Multiplying the equilibrium constant by this 55.5 molar concentration allows us to isolate the ions on one side of the equation. This product is defined as Kw, the ion product of water. The experimentally calculated value for Kw at 25 degrees Celsius is 1.0 times 10 to the negative 14th molar squared. This constant is a mathematical anchor. In pure water at room temperature, the product of these two ions is fixed. Because Kw never changes, any increase in hydrogen ions requires a corresponding inverse decrease in hydroxide ions to maintain the equilibrium. Working with extremely small concentrations, like 10 to the negative 14th, is cumbersome. It requires a more functional way to track proton levels. In 1909, Søren Sørensen introduced a logarithmic scale for expressing hydrogen ion concentration, a system we now call pH. The symbol P in this scale denotes the negative logarithm of whatever follows it. The pH of a solution is defined as the negative logarithm of the hydrogen ion concentration in molarity. In a neutral solution at 25 degrees, the concentration of hydrogen ions is 1 times 10 to the negative 7th molar. Solving the logarithm turns that exponent into a clean integer of 7. While these integers are easy to use, they represent exponential changes in the actual concentration of protons. A drop from pH 7 to pH 5 is a shift of only 2 units, but it signifies a 100-fold increase in the hydrogen ion concentration. The pH scale uses logarithmic mapping to track these massive fluctuations in the chemical environment with manageable numbers. While strong acids dissociate completely, the functional groups in biomolecules and enzyme active sites are often weak acids. Weak acids only partially ionize in water, meaning they exist in a dynamic balance between their intact and dissociated forms. This balance creates a conjugate acid-base pair. Acetic acid is a classic example. The intact acid acts as the proton donor, while the acetate ion acts as the corresponding proton acceptor. The tendency of this specific acid to release its proton is defined by its own equilibrium constant, the dissociation constant, Ka. Following the same logarithmic rule we used for pH, we define pKa as the negative logarithm of the Ka. In this system, a higher Ka value indicates a stronger acid that dissociates more readily. Because of the negative log, this translates to a lower pKa value. The lower the pKa, the higher the tendency for that molecule to lose its proton. While pH measures the current state of a solution, pKa defines the intrinsic proton affinity of the molecule itself. To map the relationship between a molecule and its environment, we use a titration curve. This is the titration curve for 0.1 molar acetic acid. It tracks how the pH of the solution changes as a base is added. The methodology involves adding a strong base, like sodium hydroxide, in small measured increments. The hydroxide ions from the base combine with free hydrogen ions in the solution to form water. As those free protons are consumed, the weak acid dissociates further to restore equilibrium, yielding more of the conjugate base. This curve provides a visual representation of how a weak acid responds to an environment that is actively pulling protons out of the solution. As we track the curve from left to right, we can identify exactly how the ratio of acid to base changes. When we reach the exact midpoint of the titration, we reach a unique state of equilibrium. At this point, the concentration of the proton donor, the acid, perfectly equals the concentration of the proton acceptor, the conjugate base. At this precise midpoint of titration, the pH of the entire solution matches the pKa of the acid. Looking at the geometry of the curve around this midpoint, the slope remains relatively flat compared to the start or the end of the process. This is the buffering region. In this zone, the weak acid and its conjugate base work together to absorb the impact of added base, resulting in only minimal changes to the pH. This mathematical resistance to pH shifts, governed by the pKa of weak acids, is what allows enzymes and proteins to maintain the specific shapes and charge states they need to function.